We may start, yes. Okay. It is a great pleasure for me to introduce Dr. Agnieszka Hejna. As we know, her PhD thesis got distinction in the International Stefan Banach competition. Maybe some biographical facts. Agnieszka Hejna graduated from the University of Wrocław in 2017. In 2021, she defended with honor her PhD thesis about Dunkl operators, and since then she is employed at the University of Wrocław, and right now she is on leave for postdoc position, 3-year postdoc position in Rutgers University. In her research, Agnieszka deals with real harmonic analysis associated with Dunkl operator. These are differential difference operators associated with a group of symmetries. So if the group is trivial, we end up with the classical harmonic analysis. Maybe some couple of achievements of Agnieszka Hejna. These are building theory of Hardy spaces, and including a proof of atomic decomposition into atoms of Kaufman-Weiss type, then study singular integrals associated with Dunkl theory and Dunkl Fourier multiplier, and associated with them theory of Liput-Pelly theory. Agnieszka Hejna has also some results about Dunkl-Schrödinger operators, including description of the behavior of eigenvalues by using Fefferman-Fong methods. These methods were adapted to the Dunkl setting by Agnieszka. And maybe some recent results. These are obtaining upper and lower bounds for the Dunkl kernel, as well as dimension-free estimates for the vector of the LP bounds of the vector of the Riesz transforms in the Dunkl setting. Achievements of Agnieszka was noticed by Mathematical Society. She got several awards, maybe because this is recorded, I will mention only sponsors. These are mBank, Polish Mathematical Society, this is Marcinkiewicz Prize, and award for young mathematicians, as well as, which is very important for us, she got distinction also by Polish Society of Women in Mathematics. This is a special prize of Edyta Szymańska. And very recently, we learned that in the edition of 2023, Agnieszka got also Kazimierz Kuratowski Award. So now, Agnieszka, the stage is yours.
Okay, so thank you so much. And the topic, my talk today will be singular integrals, and my goal will be to discuss them both in the classical and the Dunkl setting. It is not exactly the title of my thesis, but I think that it is the right time to thanks my advisor for great support and help during my PhD, or simply being the perfect supervisor. So thank you. Jacek Dziebański. And here. Can I get some help with switching with the slides, because I don't know.
On the slide, the mouse not.
Okay. Okay.
Just click.
Okay.
No.
Okay. Okay. So here you can see the plan of my talk. So first, I am going to discuss very classical things, that means singular integrals and their connection with Hardy spaces. Then I'm going to give you some ideas and main topics of the Dunkl, and finally, just briefly, I am going to discuss some results connected with my thesis, which connects both of the topics. Okay, but first, let us begin with something which is very classical, that means harmonic function, and by harmonic function, I mean the real part of analytic function. Okay, so suppose that we have the function u, which is which is harmonic function in the upper half plane, and then let us discuss the usual type of the question. And the usual type of the question is the question about conjugate harmonic. More precisely, the question is what should we assume about this function u in order to guarantee the existence of the conjugate harmonic to this function. That means function v such that u plus iv is analytic in the upper half plane, and moreover some technically looking growth condition is satisfied, so it is given in the slide, but the idea is to have a specific bound on horizontal on the integrals over horizontal.
Remove this probably.
Horizontal lines. Okay.
No.
That's
Okay. Okay, so the answer to this question is given by classical theorem of Dunkl, Gandhi, and Silverstein, and the statement is that such a conjugate harmonic function exists if and only if some maximal function is L1 function, where this maximal function at the point x is supremum over all of the values of the function u over the cone of the top at the point x0, as you can see in the slide. Okay, and then we can consider the boundary values of the function u, the harmonic function, the boundary values on the real line, or more precisely, one can consider the limit when y tends to 0 of u x y. And in the general situation of harmonic function, it is completely not clear why such a limit exists or not, but under our assumptions, it turns out that such a limit exists, and it defines L1 function. And moreover, it turns out that the function u can be reproduced from the function f, the boundary value, by the relevant convolution with the Poisson kernel in the upper half plane. Okay, and now we are ready to define the real Hardy space. So simply, the Hardy space is the space of those functions which can be obtained by taking limit 2, as in the slide, from some harmonic function u satisfying condition 1 from the previous slide. So we see that the Hardy space comes in very natural way. And moreover, it turns out that the space, which is the subspace of L1, is quite important in analysis, and in particular, the space can be characterized in many equivalent ways. So, for instance, it can be characterized by maximal functions, which is somehow suggested by Dunkl-Gandhi-Silverstein theorem. We have characterization by singular integrals, and I'm going to discuss this later on. And we have also the other characterizations, for instance, Paley-Littlewood square function characterization, which is some counterpart of orthogonality notion in the spaces which are not necessary Hilbert spaces. And we have also atomic decomposition characterization, which is, briefly speaking, way to write down the function as the convergent series of simpler function, where the name for those simpler function are atoms.
And of Hoffman should be Koyman.
Oh,
Koyman.
okay. Okay, so a lot of people made contribution here and here. I decided to give here just the origin, and here it is reasonable to mention Stein, Weiss, Hoffman, and Koyman, as you can see in the slide. But Hoffman is also in this theory, so it's the source of that thing. Okay, and then we are ready to discuss the singular integrals aspects. And in order to do so, we have to come back to the very first slide with harmonic function U. Okay, so we know that the Hardy space is the space of boundary values, but now we have also the function V. So the thing about which we can ask is the existence of the boundary value, but for the function V, the conjugate one, not the function U. And then it turns out that under our assumption, this limit exists as well. And moreover, it is L1 function. And moreover, it turns out that it can be expressed in terms of boundary values of the function f, the boundary value of U. Okay, and this way is that its value is some operator applied to the function f, and this operator in the slide is h, is called Hilbert transform. And this is the simplest example of non-trivial singular integral in real life. And here we have several definitions of the Hilbert transform. And here I decided to begin with the definition with the convolution with principal value distribution. Okay, and this is the limit when epsilon tends to 0, 1 over pi, integral over the exterior of the ball of center x and radius epsilon, fy integrated with the integral kernel, which is x minus y. Okay, and this operator is well known in analysis, and we have some well-known properties, and one of them, for instance, is boundedness result. So the Hilbert transform, the operator defines as here, is bounded on LP spaces for P greater than 1. One more classical result is that this operator is of weak type 1,1. And now we have the question about the endpoint. That means if this operator is bounded on L1, and the answer is not. So we can point out the counterexample. It's not bounded operator. Okay, so now what can be done here? So the natural thing which can be done is to consider the space of those functions from L1 for which the Hilbert transform is still in L1. And then it turns out that the space is nothing but the Hardy space defines in terms of harmonic functions. So this is what I mean by equivalence definitions. Okay, so now we have one-dimensional theory, and then we can think about n-dimensional aspect of this. Okay, and again, in order to discuss this, we have to come back to the very first slide with harmonic function U and the conjugate function V. Okay, and we know that they are connected via Cauchy-Riemann equations. So the natural thing which one can do here is to generalize Cauchy-Riemann equation. So let us introduce the notion of generalized Cauchy-Riemann equations. So now, instead of just two functions, U and V, our goal will be to consider the vector of n+1 functions in the upper half space. That means the last coordinate is positive. Okay, and then we have to define Cauchy-Riemann equations. So we have a lot of them, but the first type is that we would like to have I derivative of j function equals to j derivative of I function. So this is the counterpart of the first Cauchy-Riemann equation in the classical setting. And we have also another one, which is the sum of j derivative of j function should be equal to 0. This is counterpart of the second Cauchy-Riemann equation. Okay, and now if we have that, we are ready to define n-dimensional Hardy space. Okay, so the elements of n-dimensional Hardy space comes from boundary values of the function u0. That means that the first function from the vector from the vector of the functions satisfying generalized Cauchy-Riemann equations. This time together with some relevant growth condition, which is in the spirit of the previous one, but here I am not going to state this precisely. Okay, so now we have the definition of the space, and again we have the same thing. So we have the whole vector of the function, so we can think about the boundary values of the other functions. So it turns out that the limits, the boundary values of them exist as well, and they can be expressed as some operators applied to the function f, which comes from the first function from the vector, and this time this operator is called Riesz transform. So this is the simplest example of non-trivial singular integral in a dimensional situation. Okay, so again we have several equivalent definitions of that, but here I decided to start with principal value definition of the Riesz transform, and the reason is that this definition is analogous to principal value definition of the Hilbert transform, so I decided to place them on the common slide. So here the Riesz transform is the limit when epsilon tends to 0 of the integral over exterior of the ball of center x radius epsilon f integrated with some integral kernel, which is xj minus yj. This is coordinate of the vector divided by x minus y, the length of this vector to the power n plus 1. And in the case when n is equal to 1, it is exactly the kernel of the Hilbert transform. And again, one can ask about properties of that. And the first thing is that we can ask about Hardy spaces, and it turns out that this subspace of L1 of those functions for which the Riesz transforms are still in L1 is exactly Hardy space defined in terms of harmonic functions. And again, we have the analogs of the Hilbert transform results. So for instance, Riesz transforms of are of weak type on 1, and we have strong type PP results. That means the Riesz transforms can be extended to bounded operators on LP for P greater than 1. Okay, so now the Riesz transforms are singular integrals, the examples of them, but moreover, they also can be used as a tool in the theory of the other singular integrals, and this is associated with the fact that we have several equivalent definitions of Riesz transforms. And for instance, if we want to look at the operators from Fourier analysis point of view, we need Fourier analysis definition of Riesz transforms, which is the equivalent one. So it is definition in terms of multipliers. So the Riesz transforms are multipliers operator. And here by the multiplier operator, I mean something which is multiplication by some function, pointwise multiplication, but on the Fourier transform side. So more precisely, in order to calculate the Riesz transform of the function, the thing which one has to do is to take the function, calculate Fourier transform of that, then multiply by our multiplier, and in this case, this multiplier is minus I times psi j. This is j coordinate divided by length of psi, and then we have to invert the transform. Okay, and of course, Hilbert transform is the special case, but in this case, this multiplier is simpler because in the case of Hilbert transform, it is just I times signum function. Okay, so this is one point of view, but we have one more point of view, which is important from the point of view of operator theory, PDE, or things like that. So we know that the generic example of the operator theory is Laplace operator. Okay, so then it turns out that Riesz transform can be expressed in that way, and Riesz transforms are compositions of partial derivatives, J partial derivative with Laplace to the power minus 1/2 in terms of operators theorem. And it turns out that this definition can be treated as important because it can be treated as inspiration or starting point in order to study Riesz transforms in various contexts, not necessarily Laplace operator, for instance, in the rational Dunkl set. Okay, so here, in order to summarize this part, so we started with Hardy spaces and singular integrals in one-dimensional situation, and then we have seen the multi-dimensional extension, but of course it is not the end of the story, and we can generalize all of the things into other contexts, not necessarily Rn with the Lebesgue measure, but here the natural extension is extension to something which is called spaces of homogeneous type, and we also have seen the connection between the operators, the semi-groups of operators, so one also can treat this topic from this point of view. And of course, there are also many various directions to study this topic. And for instance, for me, one of the important point of view is multi-parameter theory, so I decided to put it here. Okay, so now this Dunkl theorem. So what it is? So Dunkl theorem is a generalization of special function theorem and Fourier analysis related to some reflections group. And the motivation was to study special functions on Riemannian symmetric spaces. So here you can see a nice picture, and the Dunkl operators introduced by Charles Dunkl in 1989 turns out to be a useful tool in study this special function, and it turns out that they have connections with the other branches of mathematics like probability theory, mathematical physics, and algebra. But the thing which is important for us is that the Dunkl operators can be treated as starting point to build up the theory of integral transforms associated with reflections group, and in particular, Fourier transform is the special case of integral transform. So in this talk, we will treat Dunkl theory as some generalization of Fourier analysis. And looking from this particular point of view, a lot of people made contribution. And here in this slide, you can see the list, but I am sure that this list is not complete. Okay, so let me give you just some ideas of this theory. So it is associated with the reflections. Okay, so we will work in the Euclidean space with the standard scalar product. And for the vector alpha in Rn, we define the reflection with respect to the hyperplane perpendicular to alpha by the formula which is given in the slide. And then we can define the main object of this theory, this root system. So the finite set of the vectors from Rn is called root system if it is invariant under all of the reflections associated with the vectors from the system. And now the finite group generated by all of the reflections is called the Weil group. Okay, so we have somehow the first parameter of this theory, but we also have something like multiplicity function, which is G invariant function, which is defined on the vectors from the root system with values in the complex numbers. But now we will assume that this function is non-negative. Okay, so we have this one. So some examples. So of course, the simplest example is in one dimension, and it is a root system composed by two opposite vectors. And of course, using that, we can construct the other product system of roots. Some of them are given in the slide in 2 and 3 dimensions, but thanks to the product structure, the analysis related to that is sometimes easier, but we have more examples of root systems. So in 2 dimensions, some examples are given in the slides. And now we are going to work with the general root system. Okay, so now let us assume that the root system and multiplicity function are fixed, and then we are ready to define the associated measure. So it is the measure with the weight, and the formula for the weight is given in the slide, and the formula is not important. It is, from our point of view, it is given in terms of root system and multiplicity function. But the important fact is that all of the function spaces which we consider here will be taken with respect to this measure. Okay, and now we can define the Dunkl operators, which are some deformations of directional derivatives, and the deformation is associated with root system and multiplicity function. So more precisely, having vector psi the direction, we can define the Dunkl operator T psi to be the differential part. That means directional derivative plus the deformation in blue by difference operator, which is the sum over all vectors from the root system, k alpha over 2. This is impact of the multiplicity function times scalar product of alpha and psi, which corresponds to the fact that deformation is taken along vectors from the root system times the fx minus f at the reflected point divided by scalar product of alpha and x, and the formula is as you can see, but in the case when the multiplicity function is constantly equal to 0, we see that this blue part vanishes, and this is the reason why we may think about Dunkl operators as generalizations of directional derivatives. And of course, they have a lot of properties analogous to the properties of derivatives, but not all of them, because it turns out that the Dunkl operators are non-local operators because of this. And for instance, the difference is that we do not have Leibniz rule for all of the function for Dunkl operators. Okay, and now we can define some elements of Fourier analysis in this setting, and we have to begin with the Dunkl kernel. So for fixed vector y, we define the Dunkl kernel exy to be the unique solution of the following system. That means the Dunkl operator on the function f should be the same as f times scalar product of psi and y, and the initial condition at 0, it should be 1. Okay, and now one can note that if we are in the classical situation when the Dunkl operators are just directional derivatives, then it is very easy to point out the solution. And the solution is the exponential function. More precisely, it is the function exponent of scalar product of x and y. So it is the reason why we may think that it is generalization of the exponential function, and this is the origin of this notation E. Okay, but the difference between the exponential function and this one is that we do not have explicit formula which can be used from the point of view of applications. But on the other hand, it turns out that the Dunkl kernel provides the extension into complex domains, and this extension allows us to generalize Fourier transform. And this generalization is called Dunkl transform, and the definition is analogous to the classical definition of the Fourier transform on L1, but we have 2 essential differences. So that the first one is that instead of Lebesgue measure, we have the associated measure. And another difference is that instead of exponential function inside the integral, we have the Dunkl kernel. Okay, and then it turns out that this is, of course, generalization of Fourier, and it is very nice. It is important. Why? Because for the Dunkl transform, we have the counterparts of many results for Fourier transform. So, for instance, Plancherel theorem and the inverse transform theorem, and the formula is almost the same as the formula for the transform itself with additional minus. Okay, so now we have this, and then based on the Dunkl transform, we can define some other objects in the setting. So for instance, we can define the Dunkl translation. So the Dunkl translation is nothing but generalization of the translation of the function by the vector in arguments. And it is defined by the analogy with the fact that the translation in the classical setting is multiplication by exponential function on the Fourier transform side. So in order to define the Dunkl translation in the Dunkl setting by the vector x, we have to take function, calculate the Dunkl transform, then multiply by the corresponding Dunkl kernel, which is generalization of exponent, and then we have to invert the transform. And we have the definition. And in analogous way, one can define the Dunkl convolution by the analogy with the fact that the convolution is a multiplication on the Dunkl Fourier transform side. Okay, so we have this. And then comparing to the fact that the Dunkl transform is nice, so these objects are not nice. So for instance, one of the reasons is that the Dunkl translations defined like that don't form a group in the sense that if we compose two translations, we not necessarily obtain the translation by the sum of the vectors. Okay, and the next problem is much more serious than this, is the problem with positivity. So we know that in the classical setting, or even under some assumptions like the assumption of being radial for the function, we know that if we have the function which is non-negative and we translate this in argument, we have the function which is still positive. But it is not the case in the Dunkl setting. So precisely we have root system, multiplicity function, vector x, and L2 non-negative function, such that the Dunkl translation of this function is the function which is negative on the set of positive level measures. So we have something which is positive, we translate, and we obtain something which is negative. Quite strange. And this is closely associated with the boundedness open problem. So first, we know that the Dunkl translations are bounded operators on L2, but on the other hand, the same question, but for other LPs or LPs is open problem. And of course, it is not easy because of this non-positivity results about this. And now we are ready to provide the connection of the Dunkl theory and the topics about singular integrals. And this connection is via nice object. That means via Riesz transform and Dunkl transform. So Tangavelu and Xu in the paper, which is indicated here, define the Riesz transforms in the Dunkl setting. And the definition is via Dunkl transform, in the sense that we define them as multiplier operators with exactly the same multipliers as in the classical sense, but this time the Fourier transform is just replaced by Dunkl. Okay, so now one can ask if it is the right definition of the Riesz transform in this setting, and somehow by some results it is suggested that it is the case. So for instance, we have the result of Amri and Sifi, and the result is that the Riesz transforms defined such a way are of weak type 1,1 and bounded on LP. And this approach is via Calderon-Zygmunt theory, and moreover, it has some applications in PDE spirit problems. Okay, so now we have the Riesz transforms, so we have the natural type of the question, and the question is about Hardy spaces. So one can define the Hardy space in the sense that the subspace of those functions from L1 for which the Riesz transforms in the Dunkl setting are still in L1, and this is H1 Riesz. And then one can ask if this space has some other characterizations, and the answer is yes. So in particular, the space can be characterized in terms of boundary values of some harmonic functions, in terms of maximal function, atomic decomposition, and square functions. Exactly the same way as in the classical case. Okay, so this is the first result. So now, if we see that, if we start with something which is defined on the Dunkl Fourier transform side, then we are able to prove something. So now we can think about generalization of those things to more general setting, and probably the multiplier approach can be helpful here. And then in our case, it turns out that it is crucial. So for instance, the starting point for studying this thing can be the analog of very classical Hermander multiplier theorem. I don't have time to go into details, but let me just state that the formulation is analogous to the classical formulation. That means we have general multiplier operator with some conditional multiplier, which is expressed in terms of Sobolev spaces, and then the claim is that the associated operator is of weak type 1,1, strong type PP, and bounded on the Hardy space. Okay. And here the crucial thing is that in the classical proof, the boundedness of the translation arguments is crucial. But here in this situation, this is not available. So in order to attack this problem, the thing which we need is somehow another approach to avoid this problem with translations. And then this new approach allows us to attack also the other types of the problem associated with the topic. So then let me just briefly mention that somehow under some technical cutoffs, one can define the singular integrals in terms of principal value spirit with some assumptions which are inspired by classical ones, and that means boundedness on the annulus condition, smoothness condition, and the limit condition. And then under some technical things, one can prove essentially the boundedness on LP spaces on H1 and weak type 1,1 results. And then from some other points of view, also the square function and Paley-Little theorem is helpful. And this approach also allows one to attack this type of the problem. Of course, I don't have time to go into details, but of course, it is not the end of the story. So for instance, for Riesz transform, we can ask about the constant in the boundedness in order to ask the natural question, which we know from the classical setting, because in the classical setting, we know that the constants are independent on dimension. So this is the first type of the question. And we know also that in the classical case, we have the dual spaces for Hardy spaces, which are BMO spaces. So it's also this point of view. And then if we have BMO space, we can ask about the operators on that. So for instance, some commutators. And of course, it's not the end of the question, which we can ask here. Okay, so now it is everything I wanted to tell you. So thank you so much for your attention.
Questions?
So you didn't mention that much about the proofs. Could you say a bit more? Is there a Calderon Siemens decomposition in this setting that's useful, or just vaguely in terms of what to think about in terms of how you deal with the non-translation invariants?
Okay, so here it turns out that somehow Calderon-Zygmunt approach was discussed before by Amri and Sifi, but here the crucial thing that we know, we have to know something about the control of the support of some function, because let us know that here we have this Dunkl translation defined, which is defined just on the Fourier side. So we don't know anything about the support of translation. So for instance, if we have the function which is supported by the unipole of center 0 and radius 1, then in the classical setting, we know that it is supported by the translated pole. But what about this transform? So we have to find somehow the way to control the support, and this is crucial.
They're pseudo-local, the local operators themselves.
Okay, so here you can see maybe for the Dunkl operators. Okay, so it's the definition. So here we have this local part. This part is called local, and here we have this deformation, and here this is the source of this being not local, because here you see that in order to calculate this the point x, we have to take into account the point which is a reflected point, which can be far away from the point x. Which this is the.
I mean, are they pseudo-local? Do they preserve singular support at least?
No.
No?
The point is that if you translate a function, the support of translation is in the orbit of the variable. But this is the first calculation, but we do not know if, for instance, LP1 is preserved. So you have LP function, you translate, and this open problem, if the LP law is preserved, even if it's not known if the translation belongs to it, unless we difficult to do. So we have to, the main point which Agnieszka didn't mention is that if we assume some regularity, some smoothness as well to the LP, then the answer is yes, and this is the main part of the proof. That's why in the multiplier theorem we have additional dimension, so we need more smoothness from the multiplier. That in the classical multiplier theorem. In the classical multiplier theorem, the smoothness is half of the dimension. Here we have dimension. And this is because we need some more regularity, and this is the main part. Main.
For other P's than one, you get different, less regularity.
If you don't do them, you need better. But this is just single argument by the qualifier. I think that's all.
The definition of the Dunkl operators dependent on the choice of the root system, and your theorem you mentioned. Is it kind of in general, because you see on n-dimensional space, you can choose either single root system or just the direct product of root system. So all the theory kind of independent of this choice.
It depends on the chart.
Yeah.
You, for example, for some theory, we fix
systems, and because you see, we do not have control. And one of the Agnieszka achievement is that if we forget about dimension, so we consider root system which are in some sense controlled by some description, but so if you change dimension, you don't have the same root system.
Yes, absolutely.
So for proving that some this transform do not depend on dimension, so one needs to have control on the constant which appear in the setting. Maybe Agnieszka will explain this better. Please, Agnieszka.
Okay, so the dependence you asked about this theorem about independence. So here the result is that in the general case, when we have nothing assumed about the function, you can prove that the bound for the norm is independent on dimension of the space Rn, but we have also this another component of the dimension. So here we have two different dimensions. That means one of is the dimension of the space, another is the dimension which is homogeneous dimension, which is here. So here, this the sum, and then one can prove that in general setting we have the bound which is dependent just on this component with the sum. But if we assume something more about function, for instance, being G invariant under the Weil group, then you can prove that it is independent also on this part about the multiplicity function. And the same result is true for Hilbert's transform. So it is independent on dimension, which is one dimension of the space, and the dimension of this one.
Maybe the last question, because we are.
And so, yeah, of course, how your theory leads to Hardy spaces because you want to have the endpoint estimate, but sometimes people somehow choose different spaces at the endpoint, like not really go all the way to L1, but through this sort of orange spaces like L log L and things like that. So do you have this sort of estimates in the theory or not?
Okay.
Okay, thank you. Maybe we can once more.
11:10. 10 minutes later.
You have to stop record.
Yes.